Hi, this presentation continues the series on multiple regression and focuses on the statistics we use to assess the relative importance and contribution of individual predictors in the model. The second level of analysis in multiple regression is at the level of individual predictors, in which our focus is the extent to which a single predictor uniquely predicts variance in the criterion. Because there is no single way to describe the unique ability of a predictor to predict the criterion, we will discuss four methods used by research to present their findings in research articles. First, we'll consider the square of the partial correlation coefficient. The partial correlation is the strength and direction of a relationship between a variable and the criterion after controlling for the effects of other predictors. By squaring the partial correlation, we are able to discuss the percentage of remaining variance in the criterion uniquely predicted by our predictor of interest after partialing the effects of all other predictors. Let's use this visual model to better understand the square of the partial correlation. If we consider predictor x2, the partial correlation squared is the unique area, u2, divided by the unique area plus error. To say another way, it is the ratio of the unique area for x2 divided by what is left over in y after partialing the other predictors or removing the variance associated with the other predictors. When we partial x1 and x3 from y, we remove those regions of y that they predict uniquely and redundantly from our consideration. So we are left only with the area predicted uniquely by x2, which is marked u sub 2, and the area not predicted by any variable in the model, which is marked by e. So the PR squared, or the partial correlation squared, is the proportion of the remaining variance in y uniquely predicted by x2. Note the emphasis on the word remaining. All things being equal, the predictor with the largest PR in PR squared will be the single most important predictor in the model. The square of the semi-partial correlation is also used to assess the importance of individual predictors. The semi-partial correlation is the correlation of a predictor with a criterion after controlling for the way other predictors correlate with the predictor of interest. Rather than removing the variance accounted for by other predictors from y, we only remove that variance from our variable of interest, or we partial the variance or semi-partial it. The square of the semi-partial correlation for a variable is the percent of total variance in y uniquely predicted by the predictor of interest after removing the variance in our predictor that is predicted by other variables in the model. Please note the emphasis on the word total. While the PR squared, or partial correlation squared, considers only the remaining variance in y, the semi-partial correlation squared considers the total area. Two important relationships is that the partial correlation will always be larger than the semi-partial correlation for a variable. Also, the square of the semi-partial for a variable is the change that occurs in big R squared when that predictor is added to the model. Let's try to understand the semi-partial correlation squared by looking at a visual model. If our focus again is on the predictor x2, the unique area associated by x2 is symbolized by u sub 2. In semi-partialing, we would remove the area in x2 that is shared with x1 and x3. Those areas are noted by the symbols G and H in this model. Although we remove G and H from x2, we don't remove those areas in y. This is what we mean by part or semi-partial. As a result, the semi-partial squared is the unique area in a particular predictor, like x2, divided by the total variance in y. Although the numerator for the partial correlation squared and semi-partial correlation squared are the same, the denominators differ. The partial correlation coefficient, partial correlation squared indicates the unique proportion of variance in y divided by the remaining variance, whereas the semi-partial squared is the unique area divided by the total variance in the criterion. All things being equal, the predictor with the largest semi-partial squared will be considered the most important predictor in the model. And when all other things are equal, the variable with the largest semi-partial squared will also have the largest partial correlation squared. The standardized partial regression coefficient is another way of identifying the most important predictors in a model. We might be tempted to use the unstandardized partial regression coefficients to assess the importance of predictors, but this is very tricky as models include variables using widely different scales of measure. But the standardized partial regression coefficients are based on standard scores, and all variables, consequently, are using the same scale. All things being equal, the variable with the largest beta will be the most important variable in the equation and will tend to also have the largest partial correlation squared and semi-partial correlation squared. There is reason to have caution, however, in interpreting beta for variables in this way, as beta can be unstable in small samples. By unstable, I mean that a variable with the largest beta in one sample may not have the largest beta in another sample. The final statistic we can discuss to understand the importance of individual predictors in a model is the change that occurs in the coefficient of multiple determination. Big R squared change is the change in R squared that occurs when a new variable is added to an equation or to the model. R squared change becomes an important statistic when we use model building methods that enter variables in steps rather than all at once. We will discuss these various methods of model building later in subsequent presentations. All things being equal, the predictor with the largest R squared change is the most important single predictor in the model. As noted earlier, the square of the semi-partial correlation equals the change in R squared that happens when a variable is added to a model. Let's look at a visual example to explain further. Here is the original model we have been considering with three predictors. R squared change is equal to the entire overlap of these three predictors with the criterion, including both unique and redundant areas. Now, let's look what happens to R squared when a new predictor is added to the model. Here we've added a fourth predictor to the model, and R squared has now changed or increased by equal to the region symbolized by J. As J is also the portion of the total variance in Y that is uniquely predicted by X4, the change in R squared equals the semi-partial squared for X4. Note also that the unique area that was previously associated with X3 has been reduced by the redundant overlap of shared variance with the new variable x4.